Welcome everybody to a slightly different theoretical physics seminar. It's different, it's not on Friday. And it's different because we have many people which I don't see that often or at all. So I'm very happy to have you here also. Welcome to us. Just some formal things if you haven't been here with us before. So we have an option. There are these flyers on every row. So people who want to ask anonymously can do so by sending the code and write with their telephone and write the question, and the question will be forwarded by somebody checking the accounts. You know, if you like, try that option also. We are trying to make it possible to communicate as in as many ways as possible. With that, I'm trying to get to the seminar. So you of course know that Brno is a city with many famous scientists who lived and worked here. Mendel, of course, is known by everybody. And Gödel, of course, is special to us, people who are interested in mathematics and physics. But today we have another person of that statue. We are extremely pleased and privileged to be able to introduce to you Professor Ashoke Sen, who is one of the absolutely most influential and well-cited people in the theoretical physics community today. So it's an enormous privilege to have him here and to have him agree to tell us about unified theories or searching for unified theories. So please, the first.
Thank you very much. Okay, thank you very much for the introduction and for inviting me here. It's a great honor for me to be speaking to you. So today my talk is going to be on the search for unified theory. So let me begin by describing what is it that I'm going to talk about. Now, science, of course, has many goals, but one of its goals is to discover the fundamental laws of nature. In particular, we would like to know what are the basic constituents of matter, what are the laws that govern their properties. And the goal of this talk will be to describe what is known about these questions, what is not known, and then how we attempt to know what is not known. Okay, and I'll try to distinguish between what is known and what is not known, okay, so that you have a clear idea of where we stand. So let me then begin by giving you a modern understanding of the building blocks of matter. Now we'll start with a material that's very familiar to all of us, the water molecule. So if we take water, then the crudest building blocks are of course the water molecules, which we call H2O. But as the name suggests, these are not the most elementary building blocks. Each water molecule is in fact made of 2 hydrogen and 1 oxygen atom. Okay, so here is the water molecule. But once we probe deeper into the atoms, we find further structure. In particular, we find that each atom is made of a central nucleus and a set of electrons that revolve around it. So in particular, the hydrogen atom is made of a central hydrogen nucleus and a single electron that revolves around the nucleus. Oxygen atom, on the other hand, is made of a central oxygen nucleus and 8 electrons that revolve around the nucleus. Now, when we probe deeper into the electron, we do not find any structure. So we declare that electrons are indivisible and we call them elementary particles. But let me emphasize that these are known to be elementary particles according to our knowledge today. Okay, later on, when we can probe even smaller distances, we may find that the electrons are not indivisible, but as of now, they appear to be indivisible elementary particles. But for the nucleus, it is a different story. One finds upon further probing that each nucleus is made of certain number of protons and certain number of neutrons. Okay, so these are smaller particles, but these certainly simplify the classification of elementary particles, because you see that instead of having many different nuclei, okay, we just have two kinds of particles, protons and neutrons. So in particular, the hydrogen nucleus is made of a single proton, whereas the oxygen nucleus has 8 protons and 8 neutrons. And then when we probe deeper into protons and neutrons, we find even further substructure. These are made of even smaller particles, which we call quarks. So for example, a proton is made of 2 U quark, or what we also call up quarks, and 1 down quark, whereas the neutron is made of 2 down quarks and 1 up quark. So it was declared that quarks are the elementary constituents of protons and neutrons. Now, so far, we have not found any further structure inside the quarks. So just as we declared the electrons as elementary particles, we also declared the quarks as elementary particles according to what we know today. So according to our current knowledge, then quarks and electrons are the elementary constituents of matter, right? Because atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons, and protons and neutrons are made of quarks. However, these are not the only elementary particles that we have in nature, because it turns out that when you collide 2 very energetic elementary particles, say 2 electrons, then we produce new elementary particles. Okay, so when we collide 2 electrons, we may find particles, we may find quarks, of course. Okay, we may find electrons, but we may also find new elementary particles. Okay, and later on, we will see the full list of elementary particles that we know today. Now, so far I have discussed the list of elementary particles. But if we really want to understand the properties of matter from the properties of the elementary constituents, then you also need to know what kind of forces operate between the elementary particles. For example, if we say that a nucleus is made of protons and neutrons, that's not enough to describe the property of a neutron, the nucleus, because we need to know what kind of forces actually operate between the protons and neutrons before we can make useful prediction of how a nucleus should behave. And according to our current knowledge, there are 4 major kinds of forces that we know. The first force that we know is gravitational force. Okay, this is in fact is what we experience in everyday life. It's responsible for Earth's gravity. It's also responsible for the motion of planets around the sun, etc. Then there is also electromagnetic force, again something which is familiar to most of us. For example, it's responsible for the force of a magnet, but it's also responsible for binding of electrons to the nucleus of an atom and so on. There are 2 other forces which you don't feel in everyday life. Nevertheless, they are very important. The strong force, for example, is responsible for binding the protons and neutrons inside a nucleus, binding of quarks inside protons and neutrons, and so on. Okay, so if you want to know, for example, how protons and neutrons make up the nucleus, we have to invoke strong force. And finally, the weak force is not needed to explain any composite particle, how particles are bound, but they are responsible for some kinds of radioactive decays. Okay? So if we want to explain some certain kinds of radioactive decays, we need to make use of the weak force. So these forces give rise to complicated interaction between the elementary particles. And the way we measure these forces is by studying how the elementary particles scatter off each other. Okay? That's the standard class of experiment that we perform to explore the various properties of these forces. So for this reason, a typical experiment involving elementary particles requires us to accelerate the particles to almost the speed of light and make them collide. Okay, and that's why the particle accelerators play an important role, okay, because they can accelerate particles to very high energy and then make them collide. Okay. And then we find what comes out of the collision. Okay. And by studying the outcome of what comes out when you collide two elementary particles at very high energy, okay, we can reconstruct what kind of forces actually operated during this process. Okay. And in that process, we may also produce new elementary particles and discover new elementary particles. Okay, so this collision serves two purposes. It first of all allows us to study the forces between elementary particles, but it also allows us to discover new elementary particles if they are present.
I think there is an anonymous question.
Yes.
Probably there is a typo. I think the asker meant which force does Higgs boson feel?
Which force?
Does Higgs boson feel?
Higgs boson feels the weak force. Okay, I am going to describe the Higgs boson in a few minutes. Now it turns out that the effect of gravitational force between the elementary particles is negligible compared to the other forces. And to see this, one can compare the electrostatic force between two protons with the gravitational force between two protons at rest. Okay, and this is a simple calculation, so I'll describe it. Okay, otherwise, I have not used too many equations in this talk. Okay, but this requires really a simple equation, so we'll write it anyway. So here is the calculation. Gravitational force between two protons at rest is given by the Newton's law of gravity. Okay, so that's the inverse square law. So G is the Newton's constant. MP is the mass of the proton, because we are calculating the force between two protons. And then this is the electrostatic force between two protons. And you see that because both follow inverse square law, the dependence on the distance cancels out, and it becomes something that is made of universal constants: the Newton's constant, the mass of the proton, and the charge of the proton. And when you substitute the values of these constants, we find a number which is extremely tiny. Okay, it's 10 to the minus 36. And that basically says that even though gravitational force is present, its effect on the elementary particles is really, really small, and in fact beyond measurement in today's experiment. And one can calculate a similar ratio for the other forces, and one finds that at the level of the elementary particles, all other forces are also much larger than the gravitational force. Nevertheless, we know that the gravitational force between elementary particles must be there, because after all, the Earth and the Sun are made of elementary particles. So if the elementary particles don't feel gravitational force, then you will not be able to explain why the Earth and Sun have gravitational force. So far I have described the list of elementary particles and the forces that they exert on each other. But this is still not enough to make any prediction involving elementary particles. So to make predictions about new experiments that we might want to design, one needs a theory. Now, what is a theory? Here is an example of a theory. Okay? This is probably something that you have already seen. Newton's law, which equates force equal to mass times acceleration. And what it does is that given a force acting on a particle, it tells you how to calculate the acceleration that the particle feels. And based on the acceleration, we can make predictions about the motion of the particle. Okay? We give the initial position and the velocity of the particle. And then Newton's law tells us how the particle actually evolves in time. So a theory of elementary particles is in a similar spirit. It is a consistent mathematical framework, just like this equation over here, which describes how a set of elementary particles evolve in time. And this theory, if we have a theory of this kind, then it can be used to make prediction for the results of any experiment involving the elementary particles. You throw in two elementary particles, and the theory tells us what will be the outcome. Now, while developing a theory of elementary particles and their forces, you have to remember two important points. And this is what makes it different from the Newton's law that you saw in the last slide. The first difference is that in typical experiments, elementary particles move very fast. Okay? In fact, they move with speed that is close to the speed of light. And because of this, we need to use what is called the special theory of relativity, which was developed by Einstein more than 100 years ago. And this theory is designed to describe motion of particles where the speeds are close to the speed of light. The second important point that we have to remember is that elementary particles are typically very small. And because if they are very small, then what happens is that if you cannot separate out the measurement from the particle. If you are a particle and if you try to measure its position, then you have to shine some light on the particle, and that itself disturbs the particle. So this makes this whole notion of a theory outcome probabilistic. You cannot make precise prediction of what happens when you take two elementary particles and hit them, because there is an intrinsic uncertainty in their position and momentum, and we need to describe them using what is called the quantum mechanics. It still has a precise set of rules, except that it, instead of making precise prediction of what happens when you collide two elementary particles, it makes probabilistic prediction. That if you repeat the experiment many times, then it gives you certain probability of certain things happening. And this is again something that you can test experimentally, because in experiments you can collide two elementary particles many times and see the outcome of all the experiments. So this is what we call quantum mechanics. Now it turns out that there is indeed such a theory, and that has been so successful that it has come to be known as a standard model. So this theory is based on the principles of quantum mechanics and special theory of relativity, just as we want. And in principle, this theory can be used to calculate the result of any experiment that we wish to perform involving these elementary particles. And as I have already emphasized, and as is clear from this name, so far the standard model has been extremely successful in explaining almost all observed experimental data. However, it has one drawback, and that is that it does not include gravity. Now, even though it doesn't include gravity, the reason that it has been so successful in explaining observed experimental data is because we saw that the effect of gravity on elementary particles is extremely tiny. And so it's not a surprise that even though standard model doesn't include gravity, it can explain the experimental data involving elementary particles, because you just don't have data that are so accurate that you can actually see the effect of gravity. So here I have given the list of all elementary particles that exist according to the standard. And here are they. So I have divided these into several classes. Okay, the quarks. Okay, we saw some examples of quarks earlier, the up and the down quark. Okay, except that we see here that there is not one up quark, but in fact three different kinds of up quark, which are denoted by U1, U2, and U3. Three different kinds of down quark. And then there are various other kinds of quarks that also have been discovered. The charm, strange, top, and bottom. Then there are leptons. Okay, this is the second class, of which we have seen one example before, the electron. But it also has something called the electron neutrino, muon, muon neutrino, tau, and tau neutrino. Okay, so these are all, again, have all been seen in experiments. The third class I'll call the mediators. Okay? These are called mediators because these are the ones that are responsible for various interactions that you see, or the various major kinds of interactions that you see in the physics of elementary particles. For example, the gluons are responsible for strong force. Okay, so as the up and down pod, for example, exert strong force by exchanging gluons among themselves. Photon is the particle that is exchanged to produce the electromagnetic force, and these particles are exchanged to produce the weak force. And then finally, there is a particle called the Higgs, and this, in fact, is absolutely crucial for the formulation of the Standard Model, even though it was not discovered for 50 years since its prediction. When Standard Model was first formulated, the Higgs particle was very much part of the Standard Model, but it took the experimentalists more than 50 years to actually discover the Higgs.
There is an anonymous question.
Yes.
Is there a reason electrons and quarks come in a family of 3?
No, there is no reason. Okay, except that if the electrons come in a family of 3, then the quarks had to come in a family of 3. Otherwise, the theory will not be consistent. Okay, so there is a reason why both have the same number of families, but there could have been 2 families of electrons and 2 families of quarks, or 4 families of electrons and 4 families of quarks. Okay, at least so far we don't know any reason. Okay, I should also add that for quarks and leptons, we also have their antiparticles. So there are antiquarks and anti-leptons. For example, the antiparticle of the electron is what we call the positron. Okay, but each of these have their own antiparticles. Gluons are their own antiparticles. Photon is its own antiparticle. Higgs is its own antiparticle. And here Z is its own antiparticle, and these are antiparticles of each other. So the antiparticle of W plus is W minus and vice versa. And I should also say that many of these particles that you see in this list were actually first predicted theoretically and then discovered. So in that sense, the Standard Model has really been successful, that it predicted many, even the existence of many new particles. And then later on, experimentalists actually found them. Now, despite its success, we know that Standard Model cannot be the final story.
Sorry, we have another anonymous question.
Yes.
What is an antiparticle?
Antiparticle is a particle which, for example, has opposite charge. It has the same mass and opposite charge, and that is a specific relation between the properties of a particle to that of an antiparticle. Just like the electron and positron, they are antiparticles of each other. Okay. Now, as I was saying, that even though Standard Model has been extremely successful, we know that it cannot be the final story. And the reason, there are some mundane reasons and some deeper reasons. The mundane reason is that there are some experimental results which do not agree with the prediction of the standard. So, for example, according to the Standard Model, the neutrinos have no mass, and indeed for a long time people did think that the neutrinos are exactly massless. But then later on, experiments showed that the neutrinos in fact have small but non-zero mass. But this difference can be easily explained by a minor modification of the Standard Model without giving up any of the basic principles. And let me give an example of, or give an analogy of what we mean by minor modification of the model. So you probably know that according to the laws of gravity, okay, if we drop 2 objects, they fall at the same rate. But if you take a ball of lead, okay, and a ball of aluminium of the same size, okay, and drop them, you will find that the ball of lead reaches a little earth, okay, falls a little faster. Of course, you have to have a very sensitive clock. So it's not quite true that they fall at the same rate. But the reason for this you can explain by taking into account the effect of friction. Okay, the fact that first of all there is a buoyancy of the buoyancy effect and then friction effect, the air friction. Okay? And once you take that into account, you will be able to explain why the ball of lead falls a little faster. Okay? This basically means that in the Newton's law, okay, you have to change. You have in the force, besides the force of gravity, you have to include the force due to the friction and due to the buoyancy. Okay. So that's the sense in which it's a small modification. You are not giving up any of the basic principles. F equal to ma is still true. Is that the F has to be modified if you want to explain this difference as to why the ball of lead falls faster. Okay. So that's the sense in which the effect of the mass of the neutrino can be accommodated in using the standard model by changing the laws a little bit. But there is a more serious reason why standard model is not complete, and that's that it doesn't contain one important force that we observed in nature, namely the gravitational force. In all present experiments, gravitational force between elementary particles is extremely small, as I've already said, and it's beyond measurement. But any complete theory must account for all forces, however small they may be. That if standard model doesn't contain gravity, then we cannot explain why Earth and the Sun have gravitational force among each other. Okay? Because Earth and the Sun are made of elementary particles. Okay? So it must be that somehow elementary particles do gravitate, okay? And that is not explained by the standard. Okay? And one way to see this is the list that I just showed you. You see that in this list, okay, there is no particle which mediates gravitational force. Okay? There are particles that mediate strong force, particles that mediate electromagnetic force, and the particles that mediate weak force, but nothing that mediates gravitational force. So then the next question will be, can we modify the standard model so as to include gravity? After all, gravity is a tiny force, right? So why not just modify the laws just as we did for accommodating the mass of the neutrino, okay, to make standard model consistent with gravity? Now, to see what the difficulty is, we have to remember that standard model is based on the principles of special theory of relativity and quantum mechanics. So if you want to modify the standard model to include gravity, then we need to first make the theory of gravity consistent with these principles. The first step, that is making gravity consistent with special theory of relativity, this in fact was carried out by Einstein more than 100 years ago, and this led to what we now call the general theory of relativity. But the second step, which is making gravity consistent with quantum mechanics, turns out to be extremely difficult. And the main difficulty comes from the fact that in Einstein's theory of gravity, the gravitational force between two objects is proportional to the energies of the objects. Now, you are probably all familiar with the fact that the gravitational force between two objects is proportional to the masses of the objects. But you also have this famous relation, right, which gives the equivalence between energy and the effective mass that a particle has. And so when you combine this, okay, with the laws of gravity, we find that the gravitational force is actually proportional to the energies of the objects. And higher the energy of the objects, stronger is the gravitational force. You combine this with quantum mechanics, which, because of the uncertainty principle, tells us essentially that we can violate the laws of conservation of energy for a very short time. So for a very, very short time, you can have, you start with a finite energy system, but for a very, very short time, their energy can go up very much. And as a result, their gravitational force also goes up. And when you finish the computation, we find that if we once you try to include gravitational force in the framework of quantum mechanics, then the answer to sensible questions turn out to be infinity. So what are the kind of sensible questions? Take two electrons, throw them towards each other, and ask at what is the probability that they will come out at 30-degree angle. Right? As I said, quantum mechanics gives you probabilistic results. You ask what is the probability, they'll come out at 30-degree angle. If you calculate this in the standard model, you get a nice finite answer. You try to include gravity, and you find that the answer is infinity. Now, this sounds a little strange because I told you that the gravitational force between elementary particles is very, very tiny. So how can a tiny force like that give infinite answer? And the reason is that 10 to the minus 36 times infinity is still infinity. Okay, so it doesn't matter how tiny the force was. Okay? Because of this infinite factor, you actually get infinite result, okay? Which of course is nonsensical because no physical process can produce infinity. So this is not a sensible answer. So this is where we stand today. This is what is known. And now we describe how to explore the unknown. Okay, what can we do to try to include the effect of gravity in this frame? So here is the central question: how can we get a sensible quantum theory of gravity? And in the rest of the talk, I'll describe the approach that is based on string theory. And we will see that it provides a possible way out of this problem. Okay, it can actually give a quantum theory of gravity. And it could also provide a possible way of combining a theory of gravity with a theory of elementary particles. But I should caution you that this is still work in progress. So whatever I say from now on, okay, is work that is theoretical work, okay, but it is still not complete in the sense that where you can make actual concrete experimental predictions that we can then try to verify. However, gravity is included in string theory automatically, okay, as we will see. So here is the basic idea of string theory. So string theory tells us that the different elementary particles, or what we think of as elementary particles, are in fact neither particles nor are they different. They are simply different vibrational states of a string. So here is a string. Okay, this is the simplest kind of string with no ends. They are called closed strings. And the idea is that a string can vibrate in many different modes. Right? It can vibrate in different harmonics. It can vibrate with different amplitudes. Okay? And these produces then different kinds of states. Okay? And the different elementary particles that you see are just different states of vibration of the string. Okay? So electron is one kind of vibrational state of the string. Photon is another kind of vibrational state of the string. The quarks are yet another kind of vibrational states of the string, and so on. Now this of course sounds strange because I told you that electrons look like particles. In fact, electrons look like elementary particles. So if this is really the case, that the elementary particles are actually string-like objects, then why haven't we seen this? The answer to this is contained within string theory. One can in fact estimate typical size of a string, and one finds that the size is extremely small, 10 to the minus 33 centimeter. And this in fact is much smaller than the length scale that we can probe in present experiments. Okay? So present experiments, the accelerators can probe distances up to order 10 to the minus 17 centimeter. So this would explain why, even if string theory is correct, the present experimentalist will see the states as just particle-like objects. It will not, present experimentalist will not be able to resolve distance scales of this kind. Now, with this understanding, we can go ahead. And note that we have to formulate a theory of strings consistent with the principles of special theory of relativity and quantum mechanics, because these are the two principles based on which we build theory of the elementary particles. And here one encounters our first surprise. It turns out that as a consequence of these two requirements, strings automatically exert gravitational force among each other. In other words, one of those vibrational states of the string produces the mediator of gravitational force. The particle that was missing in the list of particles that you have in the standard model comes out automatically just from principles of special relativity and quantum mechanics. So in this sense, in string theory, gravity is not an end. You try to formulate a theory of strings consistent with these principles, and there is no way you can avoid gravity. Gravity is automatically part of the theory. Yes.
That's an anonymous question. How do we infer the typical size of strings?
Yeah. So typical size of the string is inferred by once you said I said that it exerts gravitational force, but it exerts the gravitational force, meaning that the nature of the gravitational force it fixes, and then the typical size of the string determines the strength of the gravitational force, the Newton's constant. So knowing the value of the Newton's constant, we estimate the typical size of the string, and that's what gives us 10 to the minus 36 centimeter. Now, gravitational force still grows with energy because it's consistent with Einstein's theory. However, the energy is now smeared over the string. It's not a point-like object. Energy is smeared over the string. And it turns out that is enough to make sure that the effect of this growth is stayed. And now the answers to sensible questions turn out to be finite instead of infinite. You take two states of the string, throw them at each other, ask what is the probability that they come out at 40-degree angle, and you get a finite answer instead of an infinite answer, that as you are getting in the direct approach to quantum gravity. However, there is a catch. Now, this we may think of as a disadvantage, but also an advantage. So let me state the catch anyway. It turns out that the string theory is so tightly constrained that we simply cannot adjust it to suit our needs. It's a theory that is given once and for all. We take it or leave it. We cannot simply say that, if it doesn't work, we do something else to it and make it work. In particular, we cannot demand that the dimension of space is what you observe in nature. So you are all familiar with the fact that we are living in 3 dimensions, right? We have up and down, front and back, and left and right. But in string theory, we cannot demand that that is the case. We cannot also demand that the different vibrational states of the string behave like the elementary particles we observe in nature. Namely, can we find the state of vibration of the string that gives you the electron? It may give, but it's not something that we can demand. We cannot just tweak the laws of string theory to get the electron out of string theory. So this is what I mean by saying that we have to take what string theory gives us. So with this understanding, let's see what it gives. First of all, one finds, after detailed calculation, this is something that you cannot explain in words, but after detailed calculation, one finds that in string theory, the dimension of space is 9. Now, 9 dimension is hard to visualize. I should add that sometimes you hear the word that it's a 10-dimensional theory. So 1 dimension time is I'm leaving out. So this 9 means the 9 space dimensions. Now, 9-dimensional space is hard to visualize, right? Even string theorists don't normally visualize 9-dimensional space. But the way we describe 9-dimensional space is by using the idea of coordinate geometry. Just as in normal space, right? To specify the coordinate of a point, we need 3 numbers, right? The x coordinate, y coordinate, and the z coordinate. Similarly, a 9-dimensional space is described by saying that we need 9 numbers to specify the coordinate of a point. So while physically it's difficult to imagine a 9-dimensional space, mathematicians have no problem in describing 9-dimensional space. And that's what we use. But the problem, of course, is with physics, right? This is not what we see in nature. But this is not the end of the story. Because if this was the end of the story, then you could say that, string theory is a nice theory of gravity, but it has nothing to do with what we see in nature. It turns out that even though string theory has intrinsically 9 dimensions, it can be made to appear as a 3-dimensional space by using an old idea which is called compactification. And I'll try to explain this idea in the context of an imaginary world in which we have only 2 dimensions. Okay, and then this idea can be easily generalized to higher dimensions. So let's imagine a 2-dimensional world. Okay? There's a floor of this lecture hall, extended infinitely in both directions. Okay? And imagine that there are creatures who are living in these 2 dimensions, okay, who can only move in these 2 dimensions. But now take this 2-dimensional world and make a slight difference. Okay? Let's say I imagine that if I start walking in this direction, the space is wrapped around itself, so that if I walk, say, 100 meters, I come back to the point where I started. We say that take this 2-dimensional space as the surface of a cylinder. Okay? Forget about the interior of the cylinder. This is really 2 dimensions. Okay? So just imagine the surface of a cylinder. Okay? If an ant starts walking on the surface of a cylinder, okay, after covering a distance equal to the circumference of that circle, it will come back to its original point. Okay, that's what I mean by the surface of a cylinder. Now, if R is very large, say larger than the range of the most powerful telescopes that these 2-dimensional creatures might have, then the 2-dimensional space will appear to be infinite in both directions. Imagine that in our world, right? If I go in this direction, okay, say 1 billion light years or 100 billion light years, we actually come back to the original point. We have no way of knowing if that is true or not, right? Because we have not seen 100 billion light years. So it is certainly possible that we can have space where we have in one direction, it's periodic, okay? But the period is so big that we just don't know that it's periodic. Okay? So it will look like the infinite 2-dimensional space from our perspective. But we can now also consider the opposite situation where R is very small. And as we make R smaller and smaller, the world starts looking more like 1 dimension. And in fact, as long as R is smaller than the resolution of the most powerful microscope, the world in fact appear as 1 dimension, because you just will not be able to see this extra dimension. So the same 2-dimensional space can appear as just infinite 2-dimensional space in one limit when R is very large, and it can appear as a 1-dimensional space when R is very small. And in fact, the same idea works in making a 9-dimensional space look 3 dimensions. We simply take 6 of the 9 space directions to be small, describing some compact space K, and when the size of K is sufficiently small, then the space will appear to be 3 dimensions. So you have 3 large and 6 small directions, and an experimentalist living in such a world will feel as if you are living in 3 plus 1 dimension, 3 space and 1 time dimension, right? Because you will not see these extra 6 dimensions. Okay? I'm talking about experimentalists because, of course, which experimentalists cannot see, we also cannot see, right, in our naked eye. Okay? And as I say, that the smallest distance that we have probed today is 10 to the minus 17 centimeter. Okay? So if this distance, if this radius is smaller than 10 to the minus 17 centimeter, we have no way of knowing today. Okay? Maybe someday we'll discover that we really have these extra small dimensions, but today we'll not. So what we see, and in fact, while in 1 dimension, okay, the circle was the only possibility. Okay? Once we have 6 directions which are compact, okay, there are many different possibilities of how it wraps up into the compact space. Okay? And one class of these compact spaces which have been very useful for describing string compactification are called Calabi-Yau spaces. Okay? These spaces were studied by mathematicians for completely independent reason. Okay? But it turns out those are very useful in making 9-dimensional space look 3 dimensional. So what we see is that even though there is a single string theory, once we start compactifying, then this has many possible realizations. So a single theory starting with 9 dimensions can have many different compactifications, and these different possibilities may be regarded as different phases of the underlying string theory. Okay, and I'll try to explain now what we mean by these word phases using an analogy. So for this analogy, we go back to our starting point, the water molecules. We know that if we have a theory of water molecules, which means a theory that describes the behavior of H2O molecules and the forces between the H2O molecules, that theory has actually different phases in the form of ice, water, and steam. Ice, water, and steam. The water molecules in ice, water, and steam have exactly the same forces. If you have to write a theory that describes the behavior of the water molecules, you will write exactly the same theory. Nevertheless, that theory has these different realizations as ice, water, and steam. So these different compactifications of string theory are in a similar spirit, different realizations of string theory, just as ice, water, and steam are different realizations of the theory of water molecules. And just as the environment inside ice, water, and steam are very different, similarly, the three-dimensional environment for different choices of the compact space K will be very different. Now, it turns out that for some choices of the compact space, the three-dimensional environment is very similar to what you observe in nature. And what we mean by very similar is that it has elementary particles and the forces similar to what you see. It has particles like electrons and quarks and Higgs bosons and other particles. And of course, gravity is common in all of these cases, right? As I said, in string theory, you cannot get rid of gravity. Okay, it's exactly opposite of what you see in normal approach to quantum theory of gravity, where quantizing gravity is difficult. In string theory, getting rid of gravity is difficult. Right? Gravity is always an integral part of any phase of string theory. And so this gives us hope that perhaps string theory can not only describe gravity, but also all other forces and all the elementary particles. And this is crucial because, as I said, in string theory, you cannot change the laws. Right? You cannot say that you will describe gravity using string theory and then you put standard models separately and combine the two theories. Right? That theory will not make sense. Okay? In string theory, you have to get everything at one. Okay? You either get it or you throw away the theory. So this is the status, but so far we have not found a phase of string theory that has exactly the elementary particles that we observe in nature, and that remains an open problem. And when I say that it has to have exactly the elementary particles that you observe in nature, I mean that it has to have exactly the right masses, right charges, right Higgs particle with the correct mass of the Higgs particle, W plus W minus and Z masses and so on. That so far has not been achieved.
This question.
Yes.
Are there any experimental approaches to see if string theory allows for 6 dimensions to be so small?
Theoretically, of course, it allows it to be small, right?
But experimentally,
people are trying to see, for example, in various experiments, if you can see hints of extra dimensions, right? Well, as I said, we know for sure that if these extra dimensions are there, they have to be less than 10 to the minus 17 centimeter because we have probed that distance. But there could be extra dimensions of size 10 to the minus 18 centimeter, right? You have not ruled that out. So experimentals are certainly trying to discover extra dimensions in experiments. So far, they have not found it. And we can, in fact, push this analogy a bit further, right? For example, if you are living inside water, we could study the properties of ice by freezing a part of the water, right? This is the property that phases of the theory. And we can also do something similar with the phases of string theory. Okay, just to illustrate that what I mean by different phases is exactly in analogy with the situation here. So imagine that you are living in a phase where 6 of the directions are circles of circumference 10 to the minus 24 centimeter. Just I cooked up this number just for fun. 10 to the minus 24 centimeter is beyond any measurement today, right? So such a world will appear as 3-dimensional from our perspective. But it turns out that it is possible to create a large region in this space where inside this region, the radius of this compact dimensions is 10 to the 10 light years, right? Which is as good as infinity because we have not been able to probe such big distances today. Okay, but this is more or less the limit of what we can see in our universe, or where we can travel in our universe. So these will effectively create a higher dimensional space inside an effectively three-dimensional universe, right? Just like we can create a big block of ice inside water. So the collection of all the phases of string theory is what has been given the name string landscape. So the idea is that this is, okay, I have drawn it as a simple line, but of course the structure is very, very complicated. Yes.
There is another question. What is the number of dimensions at the boundary?
There is no short boundary. So what happens is that as you go from far away region to this region, the radius of the compact dimension slowly increases from 10 to the minus 24 centimeter to 10 to the 10 light years. So there is a sharp change anywhere. Okay, so the idea is that if string theory is correct, then we must be somewhere in this landscape. So then we can say that the problem of connecting string theory to nature reduces to finding our place in the landscape. We have studied many points on the landscape, but it is generally believed that we have really discovered a very, very small part of the landscape of string theory, right? Because there are new techniques that are coming up to discover new parts of the landscape. And the idea that if string theory is the correct theory of nature, then we should be somewhere in this landscape, that we have not identified yet. We also need to explain why we are here, right? Imagine that we find a point on the landscape which describes exactly what we see in nature. But then is there something special about that point? That's the point that describes nature, right? What about other points? So these are the questions we would like to know the answer to. Now there is a possible answer to the second question, and this may be that no single phase of string theory is special. It may simply be that our universe is very, very big, and different parts of the universe exist in different phases. Just like the example I gave with ice and water. Yes.
Can the number of dimensions 9, which is 3 times 3, has something to do with the 3 dimensions we want and the 3 types of parts electrons we have?
No, that's well, maybe once you understand our position in the landscape, we'll find some connection, but certainly today we have no such connection. That is. Okay, so here the idea is that it may be that the universe is very big and all parts of the landscape are realized in some part of the universe. Just like in a big reservoir of water, right, there may be some part which is in the steam phase, some part which is in the ice phase, and some part which is in the water phase. So these are the two words which are often used, right? The multiverse is this picture, okay, and the landscape, and sometimes people confuse between these two, right? So landscape is the idea that there are many different phases of string theory, which of course we know for sure, okay? And the collection of all those phases is what we call the string landscape. Multiverse takes it further and says that all parts of the landscape are actually realized in the universe. Okay, just different parts of the universe are in different phases. Now, I'm more or less coming to the end of my talk, but let me just say that what I described here is string theory as we understand it now. But this understanding has evolved over many years, and it has gone through many evolutions. In fact, in the mid-80s to mid-90s, it was thought that there are 5 different string theories. People try to derive the laws which are all consistent, and they found that there are 5 possible laws that are possible, okay, and hence 5 consistent string theories. Till it was realized they are in fact not 5 different theories. They are like the 5 windows into a room in which the string landscape lives. Okay, they are actually part of the same theory. Different ways of describing the same theory. So here is a rough picture of what we understand today. The string landscape is like a living in a big room, and these are the 5 string theories that we used to know. And with the help of these string theories, we can explore we can view a part of the landscape. In principle, from any of these windows, we should be able to see the whole landscape. In practice, because our computational tool is limited, through any of these windows, we only study a small part of the landscape. Okay. For example, the part of the landscape near this window we can study well based on this theory. And as we go further and further away, our vision becomes blurred. Okay. But then we study from the other window, okay, some part and so on. And much of the development in string theory has happened by studying the part of the landscape from more than one, right? Because then we learn more. And perhaps to find our position in the landscape, we need to open new windows into the room, right? Maybe where we are actually in the landscape is so far from all of these windows, right, that it's not enough, or it may be barely enough, right? And maybe by opening a new window, right, we'll be able to view our position in the landscape better, right? Which will require discovering either new ways of formulating string theory or maybe something completely different, right? Which also actually views this landscape. So this is the end of the main part of my talk, okay? But I'll just put up a slide with what I call the side stories. So like the great epics, right, string theory as it develops also has many side stories, and these involve possible application of string theory to solve problems in other real fields. One is black holes in quantum theory, right? Black holes in quantum theory pose many puzzles, which in fact existed in people's attempt to understand quantum theory of gravity independently of string theory. And it turns out that because string theory now is a good quantum theory of gravity, one can address many of these puzzles using string theory with satisfactory answers. We have not solved all the puzzles involving black holes, but we have solved many of the puzzles involving black holes using string theory. Then there is also string theory approach to solving problems in what is called quantum field theory or the theory of point particles. This is somewhat technical and I'll not go into the details, but this is also sometimes called the ADS-CFT correspondence. Okay, string theory in certain spaces is dual to certain kind of theories of point particles. And then there is also string theory applications to mathematics. It turns out that using string theory, people have found many new mathematical identities. Now, this sounds strange, right? How can a theory like string theory lead to new mathematical identities? Okay. And so let me just explain this a little bit from this picture. Okay. So the idea, as I said, that some points in the landscape, some part of the landscape can be viewed from different angles. And this means that some computation, okay, say you take two strings, throw them, and calculate the probability of what happens at different angles. Computations of those probabilities can be done in two different ways, right? You can do it from this window, or maybe you can do it from this window, or this window. They lead to a priori different answers, or different looking answers. And then you demand that if string theory is to be consistent, those two answers must be the same. Okay? They are different mathematical expressions, at least different looking mathematical expressions, but consistency of string theory demands that those two expressions must be the same. So this way, string theory has led to many identities. Okay? And then the mathematicians actually went and verified that all those identities are actually true. Yes.
There's an anonymous question. Are these 5 core string theories exactly the only 5 possible phases of string theory?
No, these are not I will not call them the phases of string theory. They are defined ways of describing the phases. Right? Each of these 5 strings, you can start with any of these 5 string theories, okay? And you can make the extra dimensions compact, which will give many phases of that theory. Okay? And those phases, and you take this theory and make extra dimensions compact. Right? Compactification of this on some space is equivalent to compactification of this on some other space. Right? In that sense, each of these 5 theories have their own phases, okay, which are describing the points in the landscape near these windows. Okay, so it's not that there are 5 phases. String theory still has many phases. These are 5 different ways of describing the phases of the theory. So I said all these make string theory rich subject to study and explore, right? If you are interested in theory of point particles, theory of elementary particles, then you study the main story. But if you are interested in something else, maybe discovering new mathematical identities, or studying properties of quantum field theory, you can use these other aspects of string theory. So let me then summarize. So what I have tried to convince you in this talk is that string theory is an attempt to formulate a theory of the elementary constituents of matter. It's based on the idea that different elementary particles are different vibrational states of a string. And I have also told you that string theory provides us with a consistent quantum theory of gravity. About this, there is no doubt. And possibly of other forces as well. This we do not know. This is the hope. But till we find our position in the landscape, right, and show that it exactly gives the standard model that we know, we cannot be sure. And that, in fact, is the most challenging problem that remains for the future. Thank you.
So, questions in person? Yes, welcome.
Yeah. So one of the main problems with quantum mechanics and gravity is the fact that quantum mechanics is non-local, right? How and general relativity has to be local, or depends local theory. How does string theory solve this problem?
Yeah, quantum mechanics is non-local in a somewhat controlled sense. The entanglement, for example, is non-local. But at the same time, it is also true that the entanglement you cannot send signal faster than the speed of light. So in that sense, it's consistent with gravity, because that's what gravity relies. Okay? That you shouldn't be able to send signal faster than the speed of light. And that's the reason why you can still make quantum theory of gravity, even though there are these intrinsic non-localities in terms of entanglement.
Yeah, okay, so maybe let me try it differently. So let's say, okay, you have some superposition of states, like a cat state, right? Of some massive object, and then you have the curvature of space-time, right? So you definitely cannot get any sensible result, because the space curvature cannot be in superposition of two curvatures, right?
Well, in string theory, it can be. In string theory, locally, right? Because curvature is just like any other quantum field, and you can superpose.
Okay, so the curvature of the space-time in string theory can be superposed.
Can be superposed. Yeah. Globally, you can. Right? The asymptotic geometry you cannot change, but locally you can superpose different curvatures.
Okay. Thanks.
More questions? Yes.
Sorry. I'd like to maybe ask, when you mentioned the multiverse as different phases, is there the dynamics of these boundaries? Is it possible that these boundaries change?
Yeah, so that is something that I should have said, but I skipped. So what? Here, there is of course dynamics of this boundary. That if these are more stable phases, the boundary expands. So in a normal liquid, right, what will happen is that these boundaries will eventually collide. Imagine that you are in some supercooled water. You form some pockets of ice. The ice is the more stable phase, so the boundaries start expanding, and eventually the boundaries will collide. Here, what happens is that if you combine this with the Einstein's equations, the boundaries do expand. In fact, they expand at local speed of light. But the medium in which these bubbles are forming, these different phases are existing, that has typically in the multiverse idea, this has a very large cosmological constant, positive cosmological constant, and because of this, that medium expands exponentially. This is not something that one sees in normal liquid, but it's a consequence of general theory of relativity. That if you have a large cosmological constant, it expands exponentially, and because of this exponential expansion, even though the boundaries are expanding at the speed of light, they never collide, or they may collide once in a while, but mostly they don't collide. Right? And so these phases continue to exist forever. But there is certainly dynamics of these boundaries.
Thank you for a very nice talk, and I would like to ask, how is the time treated in the string theory? Because we talked about the 3 dimensions or 9, and how about time?
Yeah, so time is treated, at least in the conventional framework formulation, just as we do it normally in a quantum theory, just as a coordinate, right? And evolution happens as a function of the time. Right? So it's, when I say 9, it's always 9 plus 1. Okay? So when we calculate the total dimension that is from the consistency, it actually is 10, right? But 1 is time, the rest are fixed. So time is treated in the normal, the way normal time in a quantum field.
Let me ask something. So do you think that string theory can be developed further, or how far, without any experimental data, like some experimental input that tells us, go this way, not that way, or is it necessary with at some point some experimental data?
I think both experimental data certainly will help. I mean, people are searching for extra dimension. If somebody finds an extra dimension, that certainly will help a lot in understanding this. Okay. From the theoretical side, as I said, the main bottleneck seems to be to explore the landscape, right? Find the whole landscape. If we can find the whole landscape, then either we'll find our standard model somewhere in that landscape, or you have to try that. Right? This certainly looked impossible, right? Few years ago, but with AI, one doesn't know, right? Because AI is good in handling data, right? And this is basically a problem of handling large data, right? You have to basically find ways to study this whole landscape. So I'm hopeful that maybe things will improve in the near future, and there will be a phase change of how we do string theory. But that's my hope.
Something to look forward to.
Thank you.
So more questions? Yes.
Is it the only way how to incorporate gravity to the standard model, or does there exist some alternatives? How to avoid this infinity problem?
I would say, okay, there are some attempts, right? But those attempts have not come anywhere close to where string theory has, right? For example, there is this attempt based on loop quantum gravity, right? Where you try to you don't try to combine gravity with standard model, just try to make gravity constant with quantum mechanics. Okay. And it has gone somewhat far on but what one finds is that you cannot explain, for example, how the classical limit emerges from that quantum. Right? So you have a quantum theory of gravity, but it cannot explain why 2 large masses have long-range gravitational force. Okay. So, whereas in string theory, you can certainly do that, because it's based on in some limit it becomes the normal quantum field theory, right? And there you can certainly see that why 2 large masses will have the standard gravitational force that we are familiar with. Right? In fact, the whole of Einstein's theory emerges in the classical limit of string theory.
So there's a question over there.
Thank you for the talk, and I'm wondering, we are talking about 9 or 9 plus 1 dimensions.
9 plus 1. So time is always taken.
Are we assuming symmetry? Is there a nature, or is supersymmetry necessary for?
Yeah, so supersymmetry is not necessary, but supersymmetry is useful for supersymmetry gives you more control on the theory. But for example, given a string theory which is supersymmetric, you can certainly set up time-dependent solutions which are not supersymmetric. So you can certainly construct phases which are not supersymmetric. It's just that they are much harder to control compared to the ones which are supersymmetric. Right? So for example, most of the theoretical studies that I said, where you can make a precise calculation, like the identities in mathematics, right, which come out of string theory, those are based on supersymmetric phases, because you have extreme control on these calculations, and you can get precise identities involving the calculations from 2 different phases. Okay. So supersymmetry is used for control, but it's certainly not necessary for the consistency of the theory, right? Because you can construct backgrounds which are not supersymmetric.
So I think, one more question.
What evidence do we have that gravity is fundamentally quantum?
Well, we don't have any direct experimental evidence. On the other hand, if you try to combine a classical theory of gravity with quantum theory of particles, right, I don't think there's a consistent formulation of that. And the difficulty can be understood as follows. So imagine that you say that there is a classical gravity, which means that you can measure all components of the gravitational field to arbitrary accuracy, coupled to a quantum electron. Now, for the electron, we know that you shouldn't be able to measure the position and momentum to arbitrary accuracy. But the gravitational field that the electron produces, that depends on the position and momentum of the electron. So if you can measure the all components of the gravitational field produced by the electron to arbitrary accuracy, then you should be able to reconstruct the position and momentum of the electron to arbitrary accuracy. And that will be in conflict with the laws of quantum mechanics. So these are the kind of inconsistencies that one runs into if we try to combine a classical theory of gravity with the quantum theory of electrons. Right? This is in fact the same reason that one can give for electromagnetism. Right? Even before we knew that electromagnetism magnetic field has to be quantized. Imagine that you knew the electron is quantized. But the electromagnetic field, suppose you want to try to treat it classically. Then the electric field will depend on the position of the electron, by the Coulomb's law. Magnetic field will depend on the momentum of the electron, right? Because the moving charge produces magnetic field. If we could measure the components of the electric field and the magnetic field to arbitrary accuracy, then you would be able to reconstruct the position and momentum of the electron to arbitrary accuracy. And that will be inconsistent with the laws of quantum mechanics. So these are the difficulties that one faces in making a classical gravity coupled to quantum mechanics. It may be possible, maybe somebody will find some way to do this, but at present, I think this is one reason people believe that the gravity has to be quantized, even though there is no direct experimental evidence.
Question? So it's not.
We have several on Slido actually.
Oh, we have Slido. So do some Slido.
Okay. Can string theory explain dark matter and dark energy?
Well, if we can find the correct position in the landscape, it has to explain everything. Right? So that's the point. That string theory, when you are saying that you are trying to find our position in the landscape, right? That point in the landscape has to explain everything that you know. Right? It's not enough to say that we can explain these things, but not the other things, right? Because as I said, in string theory, there is no way to combine string theory with something else. So yes, in principle, it's possible. Right? In fact, one of the things that people say about these landscape points in landscape is that any single property that you can think of in the standard model, you can get inside. You can get models with dark matter, you can get models with electrons, you can models with muon, you can get even models with dark energy, right? There have been constructions. The problem is to find a point in the landscape which has everything at the same time. That has not happened. That is the challenge.
Can you say more about the process of black holes that string theory has solved?
Well, one is the entropy of the black hole, right? Because we knew from the work of Bekenstein and Hawking that the black holes carry entropy, and it's purely a geometrical idea that they found that the classical black holes behave as if they are thermodynamic objects. And then Hawking's result of Hawking radiation actually fixes the actual coefficient in quantum theory. Because you know the black hole has an entropy towards the area of the event horizon. And the question was, can we explain that entropy in the statistical sense, log of the number of states? And this was counted in string theory in some specific context. And it was a completely different analysis, no geometry, right? Just counting in a quantum theory. And people did find that the log of that number is precisely the entropy that we calculate from geometric data.
This here already answered. What is supersymmetry? I thought string theory needs it.
Yeah, as I have said, yeah, that supersymmetry is a tool. Many of the cases of string theory have supersymmetry, and those are the ones we study most because those are the ones that have more control. Okay. And the general idea is that we start with theories which are vacuum, which are supersymmetric, some cases which are supersymmetric, and then go a little bit away from those points where supersymmetry is broken. That's where the standard our position in the landscape. It's certainly not necessary that that's the case, right? But as people say that we use the lamppost principle, right? If you have lost something, you look where you can. And the supersymmetric theories are like the lamp, right? That it's easier to study the theories near the supersymmetric case. Right? You are not certainly looking at supersymmetric case because we know that our world is not supersymmetric. But if our world happens to be close to a supersymmetric case, a supersymmetric quantum landscape, then it will be easier to study. But certainly it's not necessary that we have to be near that supersymmetric.
I read there's an M theory that has 10 dimensions. So is it in conflict with string theory?
MP?
M theory. M theory.
M theory has 11 dimensions, yeah. So that is not conflict with string theory. It just so happens that in this box that I showed, there is one corner, one point in this box, right? I mean, here of course I've drawn a two-dimensional box because that's what I could draw, right? But it's really a multi-dimensional box. And one extreme limit of that multi-dimensional box, you find that the theory effectively has 11 dimensions, 10 plus 1 dimension, 10 space and 1 time dimension. And that's what is called M. Right? So it's not certainly in conflict with string theory. In fact, the only reason we know the existence of M theory is because of string theory. Right? In this space of phases, right, we find the point where you have 10 non-compact, 10 spaces.
Last question: does string theory encounter magnetic monopoles?
Yeah, in some of the phases of string theory, you do have magnetic monopoles. Right? It depends on again what point in the landscape you are in. Right? So in this diagram, certainly there are points where you do have magnetic monopoles, but there are also points where you don't. Okay, so it's not a universal feature that all phases of string theory have magnetic monopoles, but some certainly do.
Thank you. That's all the questions.
So no more Slido, no more in-person questions. So I think this was a very beautiful seminar with a very interesting question section. Let's take all we learned home and go home and think about how to improve string theory. So for that, let's thank Professor Sen.
Thank you very much.